Yeah. So I would like to say, as the last speaker of the week, but also in my capacity as a co-organizer, just to say thank you to everybody for participating in the workshop this week. I think it's been certainly a very enjoyable and I hope useful and informative and successful workshop. I feel like I've certainly learned a lot, and I think in part this is due to the speakers this week who've given obviously a lot of careful thought to the content of their talks and as it connects to the theme of the conference and also the varied backgrounds of everybody here. And also all of the participants, I think, for just being so actively engaged throughout the week and asking great questions and so on. I think it's set us up pretty well for the second week, so for those of us that are moving up to Pingree Park, I feel that we're in a good spot and we've got lots of things to carry on talking about next week. And for those of us who are departing, I hope we will continue to have these discussions by email and so on as well. I'd also like to commend the organizers that are not me for their excellent decision to truncate the workshop today. I know I speak for all of us in the Fort Collins crowd that will be happy to get home just a little bit earlier today, and we're quite happy to move up our appointments with the Swamp Cop in the Prairie Dog Highway, is it? Prairie Dog Memorial Highway. This is an in-joke, which I apologize for, but of all the problems we've talked about this week, I would say that they all pale in difficulty to the problem of trying to predict what 15 mathematicians might actually say if you put them in a minibus for about 15 hours and see what emerges. So from whimsical hard problems, let me move on to more serious hard problems. You may recall from the last lecture, and for those of you who weren't at the last lecture, or also for those of you for whom Tuesday was so long ago you can't remember, I will do a brief recap shortly of some of the main themes from last time, the things that we need to take with us in this lecture. But broadly speaking, last lecture was about things that are easy, and this lecture is about things that are hard. And I don't mean this in sort of a theoretical sense. I mean, the easy part was sort of, in some sense, a culmination of about 8 to 10 years of work. So I don't mean it was easy to produce. What I really mean is that it was kind of easy to compute, right? So in an algorithmic sense, the things that I talked about last time are the things that you could sort of get your hands on relatively easily from a computational viewpoint. And the things that I'll talk about today are things that are rather more difficult. But the idea, if you recall, is to use the things that were easy to get your hands on to try to inform these problems, to try to attack them in some way. Okay, so quick recap then. So if you remember, we're going to deal with just bimaps for the course of these talks. So T will be a bimap from modules, vector spaces U2, U1, and U0. F is going to be a field of Q elements, and if you remember, we have this kind of operator space here. It's a direct product of all of the operators that act on the individual modules. There was a couple of rings that we introduced last time, the first one being the centroid ring, and if you recall, this was the ring, the largest ring over which your bilinear map is bilinear. And so the idea is to sort of immediately kind of rewrite your bilinear map over the centroid ring. And then this is a more natural object to look at. Yeah, so one of the upshots from last time was that I mentioned, that this was towards the end of the talk last time, I mentioned that there is this algorithm that if you're given two bimaps, S and T, in polynomial time you can decide if there is a principal isotopism between these bimaps. And I'll just remind you what that means. Remember, isotopism, and I'll put this on the next slide because that's really going to govern what we talk about today. But the isotopism is the situation where you've got operators in all three coordinates, right? So there would be an omega 0 outside here. And this is the hard problem that we'll discuss today. But if you make this into the identity, it turns out the problem is somewhat easier and you can solve it in polynomial time. And we talked a little bit about this last time. James also gave sort of a high-level categorical reason for being able to solve this efficiently, which was to sort of kind of transform from the homotopism category into the adjoint category, which kind of brings me on to the adjoint ring, which was the ring that we mentioned last time. This is the largest ring over which your tensor is bilinear, midlinear, I should say, midlinear. So you can pass scalars between the two domain components. And this is something that's going to be important to us today, because what this means is you can sort of factor your bilinear map through the tensor over that adjoint ring, and this is something that we'll do a little bit later. I realize that I think the video can see this screen actually for some reason. It never used to, did it? Or has it always been able to see? Okay, right. I'm just going to put something up on this sideboard. We're not going to talk about this much today, but if you remember, there was also the situation where we imposed a little bit of symmetry on our bimap. So I'm just going to introduce a little bit of terminology and notation, in fact, for the benefit of those who actually stayed with us and are here. So we can talk about these things called Hermitian bimaps, if you remember. These are things where you've got an additional sort of symmetry, where if you kind of reverse, it's the same module in each of these two components, and if you reverse the arguments, then you kind of pick up this kind of automorphism. And just a little bit of terminology related to these things. Principal isotopisms become isometries, and isotopisms, which we'll see soon, become pseudo-isometries. Again, I'm just kind of mentioning these names because they'll be sort of in the background. Well, we won't really use them too much. And then the other thing about this that you may remember as well is that the adjoint ring, adj_t, is a star ring. So it picks up an anti-automorphism, which turns it into a star ring, and so we study this thing as a star ring. So I'm going to talk throughout today really just about this kind of general case, not about the symmetrized case. But a lot of what I say today will apply to this more symmetric case as well. And I'll mention that when it's convenient. Okay, I can switch back now, Josh, that's all. I just wanted to leave that hanging around on the board. Okay, so the problems we will talk about today then, let's give them a precise statement. The first one is called the isotopism problem. And you can see it's the group, or really the coset, if you like, of isotopisms from a given bimap S to a given bimap T. So this is the computational problem that we want to solve. And you can see it's different from the thing that we can solve because it's got this additional operator here. And then a related problem, the autotopism group, given a fixed bimap T, we want to find generators for the group of all autotopisms, right? So isotopisms from the tensor to itself. And you may also recall that this had a nice description as this zero set with this nice polynomial x2, x1 minus x0. Okay. So in order to talk about these problems, we've talked about the idea of brute force. If you were to just kind of sit down and kind of blindly try to work out what the solution to these problems are, what would be the complexity of that task? And obviously one thing that you can do is to just kind of loop through all possible automorphisms of U2, U1, and U0. You can look at all of those triples and ask yourself if they're satisfied. But can we do a little bit better? And the answer is, well, we can. So I'm going to talk for a little bit about kind of brute force techniques, and then we'll get on to the more refined techniques that kind of use these algebraic structures a little bit more after we're done with that. So brute force version 1 then. So one of the reasons that I put the results about principal isotopisms on the first slide, and if you remember, there was an analogous result for isometry in the case of balanced bimaps as well. This was something I mentioned at the end of the time in my first lecture, and I mentioned that at the time when we sort of first saw this result, the result about testing isometry efficiently, we didn't really know why that would be useful. And so what I'd like to do is to kind of talk briefly about why it's useful to be able to test at least principal isotopism or isometry between two given bimaps. So here's the idea. If there is an isotopism from one bimap to another, what seems now a rather trivial observation is the following, that if you change your bimap T to the bimap T0 by just kind of following T by this map phi 0, then of course what you have is a principal isotopism phi 2, phi 1, 1 from S to T0, right? So what does that mean? It means that if you are searching for isotopisms, what you can really do is just search for principal isotopisms, right? You can loop through all of the automorphisms of GL U0, and then you can try to find a principal isotopism to this bimap, and if you can do that, then you can find an isotopism to the original pair of bimaps. So this gives us at least some measure of brute force in that we can list all of the elements in GLU0 and then try to lift every single one of these things to a principal isotopism. Remember that testing principal isotopism you can do in polynomial time. So roughly speaking, and I'm not going to get too precise about complexity today, roughly speaking, you can test for isotopism in time the order of the general linear group on the codomain space U0. Okay. So that's a nice observation. It's not particularly useful, of course, when this domain U0 is quite large. It's not a particularly useful observation because we're still dealing with a very large group. But it's nice to know that if you have a putative element that's acting on U0, you can at least test whether it can be lifted to an isotopism. Now, the reason that this is important, actually, and we'll get to this a bit later today, is that quite often we're in a situation where we're not trying to list all of GLU0, actually. It may be that through some hard work and cleverness, we've discovered that you can't move things around freely on U0. There may be some impediments to that. And it may be that you've actually figured out what a putative group of outer isotopisms could be, or autotopisms. And then, you've kind of cut down how many things that you're trying to search through. This turns out to be a rather useful idea that, as I say, we'll come back to a little bit later on. And I'll tell you some ways that you can try to cut down this GLU0 a little bit. Okay, so this is the first version of brute force. It's perhaps not the most familiar. Let me tell you version 2, which is in some sense kind of present in most approaches to these kinds of problems that exist. When you don't know what else to do, this is essentially what you do. So we're given two bilinear maps, S and T. And because they're bilinear, of course, we can factor it through the tensor product over the field. And by factoring it through, what I mean is that there is a linear map which sends us from the tensor product to the codomain space, U0, having this property. That's all that we mean by factoring through. And then if you kind of sit down and scribble on a piece of paper, what you realize is that a triple phi 2, phi 1, phi 0 is an isotopism between these bimaps from S to T, precisely when phi 2, phi 1 maps the kernel of one of them back to the kernel of the other one. Okay? So this gives us a means of, another kind of brute force means of testing for isotopism. So what you can do is you can calculate this tensor space. You can calculate the induced action of GLU2 cross GLU1 on this tensor space. And you can also compute these induced maps. You can compute their kernels. That's just linear algebra. So nothing I've said so far is costly at all in a computational sense. But what I'm about to say is the costly part. What you want to decide is whether these two subspaces are in the same orbit. Okay. Now, of course, this orbit could be huge, and usually is, in fact, huge. In the generic situations, it's very close to regular, if not, in fact, regular. And so really these orbits that you get are kind of roughly the order of the product of the two general linear groups. And so that's why we have this kind of roughly this time algorithm to follow this direction of brute force, where we're kind of acting on the domain spaces. But as I say, this sort of idea kind of underlies lots of algorithms that are implemented in GAP and Magma, in fact. You know, if you kind of reach a situation when you're computing automorphisms of P groups, for example, where you just don't know any more information, and the computer can't, you know, you can't, by all of the different clever techniques that you have, you can't actually determine any more information. This is usually what the computer does. Oh, and by the way, I should say that the way that these orbits are calculated is by and large what Alexander Hultke described in his talk, one of his talks. I can't remember which one. It was probably the first one, in fact. You basically treat this thing as a permutation group, right? You treat the projective space of U2 tensor U1 as a projective geometry, and you sort of compute the action as a sort of, you know, moving around points in your permutation domain, and then you use permutation group machinery to do it. This is, of course, it's happening in a linear space, but there's nothing really obvious about what you know about that linear problem, you know, to make it tractable to kind of more linear methods. And so you essentially just treat it as a permutation group problem. All right, so far so good. So they're the two types of brute force algorithms. And what I'd like to do is to kind of introduce a little bit of nuance to the second type of brute force problem, where we take this tensor product idea, but we kind of add a little special sauce. So, as I say, factoring through the tensors is a good idea. What we'd like to do, though, is to rather have a much smaller space on which to act. We'd also like to have a smaller group that acts on that space, so that this brute force calculation that we're confronted with at the end of computing the orbit is a much more tractable problem. So, the problem with using the tensor is that it's a generic space to use, right? So it's got nothing to do with the particular bimaps that we're looking at. But we can, if we just kind of focus on one particular bimap, let's call it T, there is a better thing over which we can tensor. In fact, there's an optimal thing over which we can tensor. This is the algebra that we were studying last time, this adjoint algebra. It's the larger string over which we can kind of factor through this tensor product. Okay? So it sort of makes sense to form this tensor product, and then you can recompute this induced map T hat, and you can do the same thing for the second tensor. And then you can sort of try to transport one of those kernels to the other in a smaller space with hopefully a smaller group acting. That's sort of the general idea here. Okay, so what do we want to make this thing work? Well, obviously we want this search space U2 tensor over the adjoint ring U1. We want this to be as small as possible. Okay. In fact, we want it to be certainly substantially smaller than U2 tensor U1, otherwise what's the point? So what do we need for that? Well, of course, the bigger the adjoint ring, the smaller the tensor over the adjoint ring. So you're really looking for situations where your bimaps have a fairly large adjoint ring. Okay. The unfortunate fact is that, again, generically, if you were to just kind of, well, I have to be careful what I say here, but if you were to pick a random bimap in the following way, by just kind of picking a space of alternating forms, let's say, something like this, then the harsh reality is that the adjoint algebra will almost always consist of scalar matrices, and you don't gain anything from doing this. But in many situations that you're interested in, just by the fact that you want to study a particular tensor, it's going to have some kind of structure to it that gets picked up by the adjoint algebra, and so this is really going to help you to answer questions about it. So the second thing, which is sort of goes in tandem with the first thing, really, actually, is that the group that acts on this space is smaller than, say, GLU2 cross GLU1. You want something that's, again, substantially smaller. Of course, I've not really told you what the group is that acts on this space yet, so I'll have to describe what that is, and we'll come to that a little bit later. And we also will need to know that we can construct that group efficiently. That's another problem. So there are some sort of unknown things that are going on here that I'll talk about as we go along. But these are the sort of two criteria that we really want to kind of make this an effective strategy, is to have a fairly large adjoint ring so that the tensor space is small, and then also to have a smaller group that's acting on that space so that the orbits are more under control. There is another issue here, which I've called a sort of an alignment issue. There's kind of a parallel here, I think. I don't know how good an analogy this is, but at the beginning of Clay's talk yesterday, he was talking about sort of taking tangent spaces on a manifold, right, and saying you're trying to compare these vectors in these tangent spaces, but you can't because they live in the wrong space. And the same thing happens here if you think about it, right? If you calculate the adjoint, well, first of all, if you just take the tensor product over the field, then both of the kernels that we wanted to compute live in that space, no problem. But if you sort of individualize and kind of look at the adjoint of a particular bimap that you're given and form the tensor product over that adjoint, and you do the same for the second bimap, well, of course, these things have to be isomorphic as vector spaces, otherwise you're not going to be isomorphic. But they don't really speak to each other in some ways. They're different vector spaces. And so one of the first things that we're going to have to do if we follow this approach is to kind of align them. We're going to have to move one of those vector spaces to the other, which again is sort of a close analogy, I think, Clay, with what you were saying yesterday. Okay. So before I describe what the method is then in sort of step-by-step detail, let's just have a look at a few applications. So the first one I introduced last time, this is one of the examples that I presented because it's kind of a nice example of a type of bimap that arises from a group for which the centroid is sort of interesting and for which the adjoint algebra is sort of interesting. So it's these so-called generalized Heisenberg groups. If you do the bare correspondence and kind of extract the map associated to this group, associated to commutation within this group, then what you end up with is when you write it over its centroid anyway, you end up with a bimap. I've corrected my exponents this time, from a vector space of 2m dimensional space. So it turns out to be an F form over that 2m dimensional space. So there's a nice result that's due to Mark Lewis and James Wilson, which says the following, that for these groups, they studied these groups, and they discovered that if you, at least for large enough primes and large enough n's, there is a Heisenberg group of roughly this order, such that if you look at quotients of order p to the n, right, so if you take this Heisenberg group and then you kind of look at quotients, there's lots of them, first of all. I won't say too much about how this compares to all groups of order p to the n, but basically what this is saying is there's a lot of these kinds of groups. And when I say there's a lot of them, I mean up to isomorphism, right? There's different isomorphism classes of these groups. So tons and tons of different quotients of the same order. And they give an algorithm that will distinguish when two of these groups are in fact isomorphic. Okay, so it's an isomorphism test. First of all, they kind of tell you, are you one of these groups, right? So they can recognize when a particular group that you're given is a quotient of some Heisenberg group. And given that you've got two that are quotients of the same Heisenberg group, they give a polynomial time algorithm to test if they're isomorphic. And really what it boils down to is using this adjoint tensor technique that I roughly described on the previous slide. What ends up happening here is that the adjoint ring itself is the full matrix ring. So when I said before, one of our desiderata was that we wanted a fairly chunky adjoint ring. This is as chunky as it gets. It's the entire matrix ring. So when you tensor over that matrix ring, everything shrinks down to a one-dimensional space over the field F. And now what you're doing is trying to compute orbits under a group that's basically the multiplicative group of this field extended by the Galois automorphisms of the field, which is a pretty small group. In order to get polynomial time, they still have to do some clever things, it turns out, but it's a fairly controlled group that you really understand. And these basically it harnesses all of those nice features that you would want from this adjoint tensor technique, and they're able to get actual polynomial time here. An interesting facet of this result, actually, this is I do remember when James first told me about this result, I was like, what? I mean, it seems sort of old hat now in some ways, based on some of the other things that we know. But the really interesting thing about this family, certainly at the time, but it's still interesting now, is that they're basically indistinguishable, these groups, right? So how do you usually tell if two groups are not isomorphic? You start messing around with them, right? You compute things that are pretty easy to compute, like centers, for example, or you might start trying to build character tables or something like this. You might compute conjugacy classes, element orders, what have you. These are ways of sort of telling whether two groups are not isomorphic before you really roll up your sleeves and kind of get stuck into testing if they are. Well, if you try that on this family of groups, you get nowhere, right? So the usual traditional ways of distinguishing groups are just useless. And so it makes this even sort of a more surprising algorithm, really, that it's able to pick out when these groups are isomorphic, when you just can't see it. Let me give you another application. So these are the so-called genus 2 groups. Again, loosely speaking, what these things are P groups. They're P groups G, for which when you compute their associated alternating bimap, if you write it over its centroid, you end up with a map from Fn cross Fn into F squared. So we kind of increase the exponents here. We've got a two-dimensional vector space. So for those of you who know P groups, what we're saying here you can sort of roughly think of as something whose Frattini quotient has order P to the n, and whose center has order dividing P squared, let's say. So you might say, okay, well, this is a very restricted class of groups, and in some sense you would be right. On the other hand, actually trying to find an isomorphism test for this family of groups was a colossal effort, it turned out. I don't want to get into the effort involved, but what I would like to say is why we were interested in those groups in the first place. So suppose you're given an arbitrary P group of class 2, an exponent P. Then that's going to translate into a bilinear map, Fn cross Fn into F to the G, right? So for some genus, the G stands for genus here. So this is, it sort of corresponds to the order of the center of the group. So that you can sort of think about this as kind of a typical exponent P group, right? You're trying to find the automorphism group of that group. And you're kind of stuck because if you remember those brute force techniques that I mentioned earlier on, if n is pretty big and g is pretty big, then both of those techniques kind of founder a little bit, right? So you're not going to start listing gln, you're not going to start listing glg. These things are too big. So what kind of things can you do? Well, you can start trying to restrict what the possibilities are that act on the outside. And so one way of doing that would be to just kind of project onto different two-dimensional spaces. Okay, that seems like a fairly sensible thing to do. If you project onto one-dimensional spaces, by the way, you just don't get enough variability, right? The idea is that you're trying to sort of distinguish different projections, if you will, to kind of put some restrictions on the outer space. If you project onto one-dimensional spaces, there just isn't that much variability. It's something that's kind of really just characterized by the rank of the corresponding form. But with two-dimensional spaces, you do get quite a lot of variability. And so what we wanted to do is to come up with a super efficient algorithm that could deal with this situation, the Fn cross Fn into F2, so that we could start to try to label different projections and then sort of decide, well, maybe only the identity can act on the outside, right? Or maybe just scalar matrices can act on the outside. Or maybe, some point stabilizer can act on the outside, in which case you've really kind of cut down a lot on the types of elements of GLW that you're trying to lift. And for the longest time, we sort of pursued these ideas, but not really understanding how we were going to lift them, even if we could cut them down. And that's really where that result earlier on comes in, the idea of being able to compute principal isotopisms. So that's sort of where the idea came from anyway. I'm not sure how much you might say about this in your Pingree talk, Josh. Some, perhaps? Yeah, quite a bit. Okay, so I'll shut up now then. Maybe I've said too much already. Yeah. Okay, great. Okay. Great. Okay, so let me move on to the results. So again, for this family of groups, I put the word morally speaking here. The algorithm runs in polynomial time. There is a sort of a technical aspect to this that one has to consider, but it runs quickly anyway. We've got a very fast implementation of this algorithm that runs in Magma. We've tested it quite extensively, and it really runs very well. So it's a very good practical algorithm as being a good theoretical result as well. Okay, so they're the two applications of this method. It seems sensible now then to tell you actually what the method is. So I think I've sort of described roughly what it does, but let me spell out the details. And what we really want to do is kind of zero in on what are the hard steps in using this, right? So I've described some sort of nice situations where the method works. But why does it work nicely in those situations, and what are the obstacles to trying to use it as a more general technique? Okay, so I'll remind you that the object here is that we're given two bimaps, and what we want to do is to find an isotopism between those bimaps. So step one, we compute the adjoint algebras of these bimaps. And again, let me remind you that this is linear algebra, right? So we can do this quite easily. So the next thing we try to do, step two, is to find an element that conjugates one of these adjoint algebras to the other. Now we know that if these bimaps are indeed isotopic, then you will be able to find they must be conjugates as well, so such a map exists. So if you fail to do this because you couldn't, computationally, that's one thing, but if you discover that there are no maps kind of conjugating one algebra to the other, then you know that the original maps that you had are not isotopic, and you can return false. Okay, so suppose we've solved that alignment problem now, we've kind of conjugated one to the other. We can tensor them both over the same space, which I've chosen, so adj here, we're going to tensor over that same ring. And again, we're going to compute the induced maps from that space to the codomain space U0. Again, this is all linear algebra. Computing this space itself is linear algebra. Computing these is just computing kernels. That's again linear algebra. And so step three is perfectly fine. And step four, what we want to do now, I mentioned before that I wanted to cut down the group that acts on this tensor space, but I didn't tell you what the group was. It may not be surprising to learn that the group is just the group that normalizes the adjoint algebra, right? So it's all of the invertible endomorphisms that normalize the algebra itself. And if it normalizes the algebra, then it acts on the space. So this is hopefully a substantially smaller subgroup of NU2 cross NU1 that we can then use to compute the action on this smaller space. And then the final step is really that step that we described earlier, which is you've now got a group acting on a space, you've got two subspaces, you want to decide if they're in the same orbit under that action. Again, you treat this basically like a permutation group problem and try to decide if the two things are in the same orbit. If they are, that translates into an isotopism between the original bimaps. If they're not, then you fail. So I've kind of broken this down into 5 steps. Maybe I'll just pause for a second and ask you, which of these steps should we be worried about if we're actually trying to write an algorithm here, and we hope it's going to be somewhat efficient. And I'll maybe ban those people who know the answer from answering. But what should we be worried about here if we're trying to make this thing work effectively? Which steps? Well, you're somebody who knows the answer. I just said you were barred. I just said you're barred. Yeah, so Josh said step 2. So this is the alignment problem, right? How do we actually conjugate these two subalgebras of a matrix algebra to each other? And indeed, that is a hard step. And I'll come back to that on the next slide. Anything else we should worry about? Four? Yeah, thank you, Taku. So that's a related problem, right? And in fact, if you've got some experience in computational group theory, you will identify these as being intimately related problems, right? The idea of conjugating one thing to another or computing the normalizer of a single thing, these are related, but not always equivalent problems, but they are related problems. And so actually computing this subgroup N that normalizes adj is also a difficult problem that we'll talk about. Step 5, it turns out, is also hard, but there are situations, of course, where step 5 is nice and easy. The two situations, in fact, that I described to you are examples of situations where you really have this orbit calculation under control. But, if you end up down at this step where the group N is large and the space is large, then, you're back in the same situation you were before. There's not very much we can do about that, so we won't worry too much about it. Well, what I would like to do is to at least talk about these two difficult problems here, the normalizer and the conjugacy problem. So let's state what they are. So two related problems, given two matrix algebras, A and B, and I'll remind you again that we're given these things by generating sets, right? Where if you're happy just thinking about the x's and y's as being bases of your algebra, that's perfectly fine. And the object is to find, if you can, an element of the general linear group that conjugates one to the other. And then the related problem, of course, is calculating this norm group, right, of the elements, all of the elements of GL that normalize a single matrix algebra. And what we're proposing to do here is to use the structure of a matrix algebra that we discussed in detail in the last lecture. And again, for the benefit of those who perhaps weren't at the last lecture or who have forgotten what we were talking about, what we can do is we can calculate the Jacobson radical. This is if you remember, the intersection of all left ideals or the intersection of all right ideals. We can compute a semi-simple complement to that radical. We can decompose the semi-simple complement into minimal ideals. And then we can also constructively recognize those minimal ideals, which is to say each one of these is going to be a full matrix algebra over an extension field. We can discover what the extension field is, and we can form inverse isomorphisms to and from. So the idea being that many of the problems that we might be interested in regard to A, we can simply write down the answer to the problem. That's sort of why we want that constructive piece. All of this can be done in polynomial time. If you remember, what really underlay all that was the use of the metax. There's a lot of theoretical algorithms that have been developed throughout the 90s, but in terms of fast implementations of these algorithms, it's the metax that underlies all of this. Okay, so last time the Jacobson radical didn't really pose too many problems to us. If you remember in the star algebra case here, there was a slight problem with the radical that we had to take care of. And you may recall also that we barred the characteristic 2 fields from that for that reason. But by and large, the problems that we were talking about last time didn't really depend too much on whether there was a radical or not, right? Unfortunately, that's not the case any longer. So let's talk about some obstacles. So a while ago when James and I were sort of interested in solving this problem for practical reasons, the practical reasons you now understand, we were confronted with certain types of algebra, and I'll get to which algebras we were confronted with shortly. But we realized we just didn't know how to solve this problem. So we spent quite a lot of time kind of thinking about how do you solve this algebra conjugacy problem. We kind of knew, of course, that this in general is a difficult problem. One of the things that we did, if you sort of combine what we did with earlier results of Saxena, we were able to prove that graph isomorphism, in fact, reduces to algebra conjugacy. So algebra conjugacy is at least as hard as graph isomorphism. About a week ago, in communication between the organizers, Josh Groschow informed me of this new result, hot off the press. So hot, in fact, it doesn't exist yet. Right? So, yeah, really hot. Still on the press. That's a better way of putting it. Thanks, Chris. So it turns out algebra conjugacy is, in fact, polynomial time equivalent to isotopism, and various other problems too. But what I wanted to stress is the very problem we're trying to solve, right? So there's that. These are the obstacles. But of course, what kind of algebras are you going to be dealing with in the context of this, right? So whenever you've got these kind of reduction problems, you sort of create pathologies to kind of make the reductions one way and the other, right? So there's no reason to suppose that the algebras that were used to make this sort of polynomial time reduction are actually algebras that you're going to be facing in real life. That's a practical viewpoint, but then there's also a theoretical side question, which is, which kind of algebras do in fact arise as adjoints of some bilinear map? I don't know the answers to this question. Or which kind of commutative rings arise as centroids of a non-degenerate bilinear map? So there are some interesting questions out there that I don't know the answer to, but we sort of press on and say, okay, well, what kind of families of algebras can we work with? So let me begin with sort of a toy example that sort of illustrates some of the things that you need to think about. So when I say toy example, I wasn't kidding, right? So this is a GL 2x2 matrices over GF3. We've got these two algebras that are generated by single elements. The first algebra generated by this 2x2 matrix. The second algebra generated by this 2x2 matrix. If you calculate their minimal polynomials, they both turn out to be irreducible over Z3. These are both fields, so they're both fields of order 9. And so they're conjugate, right? But how do you conjugate them? Well, this is a stupid question as I've posed it here, because GL23 is how big? Not very big. Should know the answer to that. 24, is it? It's small anyway. The point is that you can, in this particular case, you can list it. You can list all of the different possible invertible elements and ask. I should point out that you can't simply conjugate x to y, of course, because they're not conjugate. They've got different minimal polynomials. But the algebras are, how do you find the conjugating element? This is kind of an interesting problem, if you've not thought about this before. Right? It's, we now generalize and say, well, let's suppose you've got two matrices x and y that are defined over GFQ, the d by d matrices. Their minimal polynomials are irreducible, degree d. We know that the algebras they generate are conjugates. How do you find the conjugating element? So this is like a baby example of what we're trying to do, right? Because we're trying to solve for fairly big classes of rings. We should at least be able to do it for fields. Well, I've got a solution to this in this part of the slide right here. Do you like it? I don't want to spoil your fun, actually. It's kind of a nice thing to think about this problem. So I also didn't want to deprive you of the solution if you just wanted to look at the solution. So what I'm going to do now is very quickly skim through the solution. Not skim, I'm going to go and on to the next slide. And that way, if you're really interested, you can kind of go to the slides, which will be posted, right, Josh? They'll be available. And you can actually look at the solution of this. Alternatively, you can look in a paper that James and I wrote a few years ago. You might be the only ones who did. So here it is. You like it? Yeah. So what can we do then? So we can solve the field problem. I will give you that much at least. It can be done. And so you can then say, well, what more can you do? And so the next thing to think about is perhaps cyclic algebras, so things that are just generated by a single element. They don't necessarily generate fields, but they're some quotients of a polynomial ring. These were, by the way, the kinds of algebras that we had to deal with in the context of the genus 2 result. So we really had to solve this problem. And the thing that delayed the production of that to a great extent was not knowing how to, So we kind of shelved it for a while, wrote a different paper, and then came back to it a bit later. So we can solve this now in polynomial time. Similarly, if you are a semi-simple algebra, how am I on time here? 15 minutes or so? I may finish early here. If you are a semi-simple algebra, then you can, so now you're kind of forgetting about the radical in that decomposition, right? We've just got these minimal ideals. We've got a decomposition into minimal ideals. And we can use that, it turns out, to calculate the conjugacy and normalizer. So if we just talk about the normalizer problem for a second, you've got these ideals, you know when they're isomorphic to each other as ideals, but that's not good enough information to be able to write down the normalizer. You need what's called isotypic components, really. It sort of boils down to this, actually, something like this, that so we've got two minimal ideals in each of these algebras. They're both isomorphic to a field, but you can't conjugate one to the other, right? Because they're represented differently. And so this is the sort of information that you need to sort of pick up in addition to knowing what the isomorphism types of the minimal ideals are. You need to know how they're represented. But if you do, it turns out that's enough, and then you can decide if algebras are conjugate. You can write down, when I say write down, again, I mean that. You can literally write down generators for the normalizer, provided that you've picked up all of this other additional information about the algebra and about how the algebra is represented. You can quite simply write down generators for the group normalizing the algebra. So that's quite nice. Any questions so far? It's possible I only have one more slide. Closing remarks, that would indicate I do only have one more slide. But I do have a few things I would like to say here. So we've talked about some of the applications of this adjoint algebra. There are others. Others sort of emerge all of the time. There's quite a few things I didn't say about the adjoint algebra in regards to what they can tell you about bimaps. But one of the things that sort of emerged fairly recently is... oh, I've got the wrong thing there, haven't I? I apologize. I think at the last minute I actually interchanged the order of these two steps. So, okay, let me say something about star algebras then, since I went to the trouble of putting this stuff over here. All of the things that I've said about semi-simple algebras is also true about semi-simple star algebras, right? So you can compute normalizers and conjugacy of these sorts of things, but remember that now, in addition to normalizing the algebra, you also have to commute with the involution on the algebra as well. That's sort of one of the things that we need for our applications. And you can do all of this stuff. There's sort of a natural description of that. It was the second point, I think, that I wanted to mention. Yeah, so recently adjoints have been used in a slightly different way to, again, sort of refine a brute force search for isotopism between two bimaps that sort of leads to a sort of a fast average case algorithm. Let's say fast this time in the Cayley model, so sort of linear in the order of the group, right? I don't want to say too much about this, but for those of you that are going up to Pingree next week, I believe that Yinan is going to talk about some aspect of this. So Yinan Li and Yuming Chao had an initial version of this result in a paper, and then there's an improved version of the paper that I believe Yinan will talk about up in Pingree. If you're not going to Pingree and you're interested in this result, then you can find it from both of those authors. And then the last thing I'll say, and this is rather a large bullet point actually, but this method that we've called the adjoint tensor, as you've seen, is something that's based on the adjoint algebra. As you've also heard this week, a more natural algebra to work with bilinear maps that you can extract from linear relations is the derivation algebra, which is a Lie algebra. Okay? This is a better object to work with, but how do you work with it? So it turns out there is another space that you can work with. It's something called a denser space that you may recall seeing in some of the talks earlier this week. Again, something that can be computed using linear equations. A little bit more difficult to compute this space, but nevertheless you can actually compute it with linear equations. So you can certainly compute it in polynomial time. You can compute the derivation algebra in polynomial time. And there is another method that's kind of based on this idea where you take the normalizer of the derivation algebra and you act on this denser space. And again, you try to compute orbits. Now the idea here is that the normalizer of this derivation algebra is smaller than the algebra you would get if you were to look at the normalizer of the adjoint algebra. The denser space is going to be therefore smaller as well. And so the idea is that the resulting orbit problem that you have is much more tractable again. So a couple of things about that. There will be a preprint available on, well, I don't say it, on archive at some point, yeah. Our goal is to do it this summer, right? So this is a joint work with Josh Maglione there and James Wilson. The goal is to get this thing on the archive at some point this summer. It's the goal. There are problems though, because we're dealing with Lie algebras here, so things are more complicated. And in particular, the normalizer and conjugacy problems are more complicated in this setting than they were in the associative case. And just to give you a little sniff of that, I've sort of waved my hands here at the fact that normalizers of semi-simple associative algebras is something that's highly tractable, right? With all the machinery we have, we can solve that problem. That's not true of Lie algebras. And in fact, Josh Groschow in his PhD thesis proved, in fact, that graph isomorphism reduces to conjugacy, not of Lie algebras in general, but of semi-simple Lie algebras, right? So this is, they're just more complicated beasts. And in some sense, that's the least of our problems, right? We actually, in practice, we really need some fairly fundamental things that we have in the adjoint case, in the associative and star algebra case, but we don't have in the Lie algebra case. So that's really work for the future. I just wanted to mention it. And also sort of a call to arms or an invitation to participate if there are those who know more about Lie algebras than we do, and I suspect that's quite a large set of people. We would invite any ideas that you have. So, thank you.
All right, questions?
How quickly can we get home? Yeah.
So, right, the question of the conjugacy of these adjoints, how, I mean, just in your experience, like how big do the adjoints tend to be, and like what kind of structure do they have? I mean, do they, are they frequently semi-simple, or the radicals versus zero? Like, is it, even if you don't have theorems, you have some sort of experience that suggests that maybe adjoints have some structure that could make it more tractable?
Yeah. So the question is, what is our experience of the structure of the algebras that arise when you take adjoints of a bilinear map? And the first thing I would say is that, again, generically, if you sort of compute bilinear maps at random by some measure of random, then our experience is that you get scalar matrices. It's rather easy to deal with, but also not very useful from our point of view. I don't know if we have much sensible answers for you aside from that, really. Maybe James has got something to say. Looks like he does.
Yeah, so either they did construct a reduction and take any associative algebra, find a n by n or 3n by 3n by 3 tensor whose algebra is a dimensional algebra.
So basically anything then. So
anything
yeah.
That's associative, but much higher dimension.
Yeah. So that sort of answers the question that I posted on the side then, really, earlier.
Without telling the representation.
Yeah.
So
Yeah.
you don't know the representation yet.
Right.
Much larger dimensional.
Yeah.
So in some sense, you should prepare for the worst, but maybe just the worst.
Taku.
So is any of this is going to advance progress for group isomorphism?
So the question is any of this work going to advance progress for group isomorphism? Well, what it has done, as you've seen, is that it's not answering the general question of group isomorphism, but what it is doing, I think, is kind of picking off some fairly important classes of groups. Right? It's giving very efficient ways of handling certain classes of groups, which then sort of helps us to slowly but surely kind of zero in on what are the real obstacles underlying group isomorphism. So I think in that sense it's been helpful. Are these methods alone likely to solve the entire problem? Then no, I would say. But they have been helpful in making progress for sure, yeah. Chris?
A really naive question. So algebraic spectrum, if we have quasi-groups, aka Latin squares, which are, before I walked in here this week, the only place where I've heard the phrase is isotopy. So are there known algorithms for telling whether two Latin squares are isotopic? I mean, where we get to shuffle the rows, we get to shuffle the columns, and we get to permute the colors or numbers.
Right, so again, for the purposes of the video, the question was, are there algorithms that determine isotopy of given Latin squares where we have more freedom to permute? I might defer to others who are more expert on this, that particular question.
Yeah, so Latin squares themselves have small generating sets. Some cases, in terms of the precise thing, I think quasi-groups do have log-n generating sets, so they still have an n log-n trig. In general, setting groups don't, so one has to be careful which axioms are controlling the small generating set. That's really the heart of it for Latin squares. There's no classification or shortcut at all.
So there's some kind of log-n algorithm where it gets log-n generators.
Right, and so this is in Miller's original Anton log-n paper, as he describes various types of data, Steiner systems, and groups is sort of the one that inspired me to look at it. Quasi-groups also have a log-n generating set, as do groups and so forth. So it's the existence of inverses gives you this trick of producing small generating sets. Failure to have inverses then turns out to be basically equivalent to graph isomorphism. So you have the ability to actually graph isomorphism is semi-group isomorphism. So that seems to be the dichotomy of where you have enough algebra. If you have inverses, you at least get this cut down. But then there's not been any sensible additional structure.
Do any of the other organizers want to say anything else?
Well, first,
before?
let's thank you. Yeah, so I wanted to echo Pete's comments. I thought we were doing it after his talk, but he kind of jumped the gun.
Sorry about that.
Yeah, thank you all for